This was requested by one of my English students actually that's also doing methods. So for anyone who's doing methods, this should hopefully be of help. If you're not doing VCE methods though, and you're just doing like some kind of calculus course, then anti-differentiation and integrals should come up, and this will hopefully be kind of helpful. So the first thing is that we're going to go through is just anti-differentiation by first principles. So we're going to look at what it is and why it can actually calculate the area under a graph really accurately. So to do that, we're going to start with the left and right endpoint method of estimating the area under this curve f of x by using the rectangular method. So to explain that, I'll just set this up here. So if we were to try and estimate the area under this curve, we might, for example, kind of chop it up into parts of certain widths. So the widths here would be, in this case, we're going to go with the intervals of just 1 at a time. And we're going to draw out a rectangle, and what I'm going to do is make the height of the rectangle be determined by the left side of each of the intervals. So on the first one, the left side has a height of 0 on the graph, so we're not even going to see a rectangle there at all. It's just going to be a line. The next one though, we're going to go up to meet the graph, and then this should allow us to draw a rectangle like that. And you can see then when we shade it in, we've got some of the area under the curve but not the full thing, and we can just kind of keep doing this. Hopefully this one doesn't go wonky on me. There we go. And I'll just move that over slightly. And there we go. And we can see that from 0 to 3, we've roughly estimated the area under the curve. But the problem is that we've still got this massive underestimation. We've got all these blank spots here all the way through, so we've got to account for that. So we could also instead do an overestimation by using the right endpoints instead. So what I'll do here is change colors, and if we go all the way up now on the right side, and we're going to go to the left, see it's now overestimating the area under the curve. But if we keep going, then we meet the graph and we get another one, and then this one here will actually overlap to here, and then the green area would be an overestimation of the area under the curve. So neither of them is very perfect, but what we could do is we could say, well, what if we average them, because one's an overestimation, the other one's an underestimation. So we could say that the left endpoint method area plus the right endpoint method area divided by 2 would then give us the average area under the curve, right? And you can imagine that the left endpoints, which were the blue rectangles, would have been 0 plus, and then this one here would have been a width of 1 multiplied by the height, which was determined by f of 1. So really it would just be 1 times f of 1 plus, and then the other one would have been 1 times f of 2. So we'll just write f of 2 like that, and then add on. And then for the green, for the right endpoint, again, they've all got widths of 1, so width times length, width times height, however you want to think of it. 1 times, this times it'll be determined by f of 3. So I'll go backwards, doesn't really matter about the order, plus 1 times f of 2 plus 1 times f of 1. And obviously f of 0 didn't get to count here because we're taking the right endpoints. And then we could divide that up by 2, and that would give us the average area. But it would still not be perfect because it would be assuming a linear approximation between them, right? In fact, we'd be getting something more along the lines of, you know, not even a curve. It'd be kind of like making little triangles from corner to corner through this box here, and then finding the area under each of those triangles. And you can still see it's not perfect all the way through as well. So instead, if we remove that, we can see those are only good for estimating. But what if instead we made the widths a little bit smaller? So we do the exact same thing, but we take a smaller interval now. If I chop that, for example, into halves now, so half, 1.5, so 3 on 2, and then 2.5, or 5 on 2. This is not cooperating with me, not too sure why. 5 on 2 like that. And we could instead now try to do the rectangle method again. I'm only going to do the left end point. You can imagine you could do the right and average it again. What we'll find though is the error margin is going to be much, much smaller. So the first one's going to be 0, the next one's going to be here. The next one then is going to be here, and so on. So you can still see it's still underestimating on the left in this case, but the amount of underestimation is much, much smaller. So we've gotten more accuracy if we reduced that interval. And so instead what we're going to reveal now is that really that interval that we're using consistently is going to be our dx, right? So same thing as you've seen in derivatives, dy dx. It means a very, very small change in x. In first principles of differentiation, we call it h, and we let it approach 0. So if I was to keep reducing those intervals and make dx approximately 0 or approach the value of 0, we would effectively see, and I might just move over here, effectively see infinitely small or infinitely small widths on rectangles going up to reach the graph. And if I was to do them infinitely close to each other, then I would effectively be drawing a bunch of lines of height f of x, and then they would effectively be shading in the exact area underneath the curve. And obviously you could do it down here, it's just not a lot of space, but and you go blah, 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 and you could do it all the way through, and then you effectively would just have shaded in the area underneath the curve. So long as dx is approaching 0, then we have a much, much more accurate measure. And this is where then integration or anti-differentiation by rule comes in. The other thing to keep in mind is that if we were to add all of these, we're effectively saying the sum of f of x, right? The height multiplied by some width, dx, so area is length times width for those infinitely small rectangles there. And then we're adding up all of those areas, and this becomes the area under the graph. And then when we look at the actual rules, we see that it's written with the integral sign of f of x dot dx. So really this here really does mean the sum of across some interval, which we'll get to. And so it's still agreeing with the first principles concept of rectangles and estimation. It's just that it's far more accurate because we're actually letting dx approach 0 now. And so if we come into the rules, you can see I've got on the side here from some notes the different methods that I use for anti-deriving different rule types. I will point out this one here is for logs. So we don't have to worry, at least in VCE methods, we don't have to worry about anti-deriving log functions unless you're doing things by recognition. And so the first one there in purple is polynomials, and this is the most common. So any polynomial function where it has terms in the form ax to the power of n, all we do is reverse the n minus 1 rule from differentiation. So I like to think of it as write it as it is. So you write it as it is, and as soon as you get to the power, add 1 to the power, and then divide by that new power. And this will be the integral of any polynomial with respect to x, like that. So for example, we could take, let's say that we've got, well actually we won't worry about f of x. Let's say that we want to anti-derive 2x cubed minus 3x. We can even do it with like negative powers and that kind of thing. Dot dx, we're just going to apply that. So write it as it is, add 1 to the power, so it goes up to 4, divide by the new power, and then we'll clean it up in the next step. And then here, take away 3x, we're going to add 1 to that power, you get a positive half, divide by the new power. And then because constants derive to 0, when we're anti-deriving backwards, we have to factor in there would have been some constant when we don't have terminals. So we always put plus c, and if we don't have any extra information to then solve what c is, we just leave it as plus c to acknowledge that some constant. It could be 3, it could be infinity, it could be anything. It would derive to 0. So when we're anti-deriving backwards, we don't know what it's coming from. So we just write c. And so then if we clean this up, 2 over 4 is a half. So we can just write half x to the 4. And over here, 3 divided by a half is 3 times 2, so negative 6. And then x to the half is the square root of x if we want to express it like that. And then plus c, and we've applied it to even a more complex polynomial. The second one then is exponentials. And these are probably the easiest because basically you just don't do the plus 1. So you just kind of skip step 2. So you write it as it is. So let's say we have, I'll do it in general form, ae to the nx. Then we write it as it is. And then don't add 1 to the power. It stays exactly like that. And you just divide by the n value, not the whole power. So just divide by n down like that. And so really it's like a on n e to the nx. So again, if we do an example, then we might have something like you know, we want to antiderive 3e to the, let's do a negative as well, negative 2x. We just write it as it is, divide by the coefficient, and so really that's the same thing as a negative 3 on 2e to the negative 2x. So that's it for the exponentials. As I said, logs, we won't have to worry about anti-deriving those by any kind of rule. The pink section then is all of your circular functions. So there's a couple of steps here. The first thing is to note that when you derive sine of x, it goes to positive cosine of x. And as long as you know that, you can work everything else out. That implies that everything else is opposite. So the derivative of cosine of x is negative sine of x. That one flips sine. If you try to integrate sine of x, right? The derivative of sine of x stayed positive. The antiderivative of sine of x will not. That'll flip to a negative cosine of x. And if we integrate cosine of x, that one now, it used to flip in derivatives. Now in the opposites, it's not going to flip. It's just going to go to positive sine of x and vice versa. But obviously there could be transformations applied to them as well. So what we do is we divide by n. So if we have something like a times sine, and we'll do nx plus b, like that, and we want to antiderive that. So the first thing we do is divide the n out the front. Then we deal with what sine does. Does it go to cosine, or does it go to negative or positive cosine? And in this case, it's going to go to negative cosine. So we're going to put a negative out the front as well. I'm going to piece it together, cosine. And the good thing is the brackets always stay the same in these. We've already factored in the n, and it's good to go. Again, if we were doing something like secant squared of x, we know that the derivative of tan becomes secant squared of x. So it works the same way. You just have to know that secant squared antiderives back to tan. So if you had, let's do a more complicated one, 3 on 2, and then we'll do secant squared of half x plus 3. So the first thing that we would do is write, okay, 3 on 2, we're going to divide out the n, which is a half. We'll deal with that later. Secant then becomes tan, and the brackets stay the same. Like that. And then we can clean up the front here. 3 on 2 divided by half gives us 3. You can also times and flip. And now we've got the antiderivative of that one as well. So then the next ones, this is where people usually get a little bit more stuck. This is where we have composite functions. So in derivatives, we use the chain rule. In antiderivatives, there's two different methods. It depends on what the power is. So if we have something ax plus b to the power of n, it really depends on what this power is. So if n is equal to negative 1, then technically we're dealing with a hyperbola. All right, that's the same thing as 1 on ax plus b. So sometimes they express the questions like this, and we want to think of it in this way. So this one, it's just follows a direct rule. There's a little bit of memory in it. It's 1 on n, and then you multiply that by the natural log of the modulus of ax plus b. And that one, unfortunately, is just straight up memory on that one there. The second case is when n does not equal negative 1. So it can be positive, it can be negative, as long as it's not negative 1. So let's say, for example, we have ax plus b to the power of 3. So this one, it's kind of like the polynomial form. You just add a fourth step of divide by the a value. So you write it as it is. You add 1 to the power. You divide by the new power, and you also divide the a down as well. And then it's good to go. But let's say it was like something, 3x minus 11 all to the power of negative 2, for example. Then what you would do is write it as it is. Add 1 to the power becomes negative 1. Divide by that new power. And then when you're dividing a fraction by a whole number, it just multiplies down to the denominator with it. The 3 will come down as well. So that gives us a negative 1 on 3, effectively. We can kind of clean it up a little bit like that. And really, we could write that as a hyperbola as well. So we could write, not like that. We could write negative 1 on 3 times 3x minus 11. And we get kind of like an augmented hyperbola function. Finally, the last two there, they're more algorithms for when you're dealing with product functions or quotient functions. There's no direct rules, so you pretty much just expand the brackets in product functions, and then you should be able to antiderive by rule, usually the polynomial form. If it's a quotient function, then you divide each term by the denominator. You'll get individual terms in polynomial form, and then you'll be able to antiderive that using the polynomial form as well. And there we go. So that is everything there in terms of antiderivatives, indefinite antiderivatives. So we move along now to definite integrals or definite antiderivatives, and this is where we actually have terminals. And so the great thing about these is that we don't have to worry about the plus c because it'll cancel out effectively. So if we want to integrate or antiderive, we'll treat them as interchangeable in the subject. Something like ax to the power of n with respect to x, and we want to do it from, let's do 0 to 3. That was the same as our interval in our graph. If you remember, we had this and we were trying to find the area between 0 and 3. So this is your left limit and your right limit, or your lower bound, your upper bound, sometimes referred to as. So the first thing you do is just integrate by rule. So that would be add 1 to the power, divide by the new power. And then the notation is you put square brackets around it, put your terminals out here now, and you're effectively going to find the difference between this expression when you sub in 3 in with 0. So this would mean, obviously we don't know what a and n are, so that's not going to be shown, but 3n plus 1 over n plus 1, take away, and then this one here, a times 0 to the power of n plus 1 over n plus 1. Obviously, subbing in 0 is going to give you nothing. It'll cancel out, but that's the general process. The reason why we don't put the plus c is because if we did, it's going to be in both brackets, and it's going to then cancel itself out. So we don't have to worry about that at all. So let's do an actual example. What I'm going to do is run through an actual set of VCAR questions from the sample exam, exam 1. Okay, so we've got this one here. So the first thing is we have to recognize what's it asking us to do, and then also what type of function it is. So this one here is technically a chain rule or a composite function. So we can rewrite it. We want to find the antiderivative, but instead of writing it like this, we're just going to write it in polynomial form. So 2x minus 3 to the power of negative 3. And what that means is this is a case where n is not equal to negative 1. So we're going to follow this 4-step method. So that means write it as it is, add 1 to the power, divide by the new power, and then also multiply down in there the coefficient of x, which is 2. And then suddenly, and actually indefinite integral, we have also got to put the plus c. So we'll do newspaper columns, and here we're just going to get a negative 4. So I'm going to put it as a negative 1/4 2x minus 3 to the power of negative 2 plus c. And because we don't like negative powers where we can avoid them, we're going to write that as negative 1 on 4 times 2x minus 3 positive 2, and then just the plus c at the end. You'll need the plus c to get the full marks. After that then, we've got the function with the rule g of x has a derivative given by this, find g of 1, or sorry, given that g of 1 is equal to 1 on pi, find g of x. So what this means is we're relying on the fact that antiderivatives are the opposite of derivatives. So if we're given g prime x, we can antiderive with respect to x to get to g of x. And that's what we first have to do. So g of x is going to equal the antiderivative of sine of 2 pi x. Now this one is a circular function with respect to x. I should have put dx on that one as well, actually. And so this one here, we go, all right, sine becomes cosine, but it flips into a negative, right? And then we also divide the coefficient of x, which is 2 pi. I'll just sneak that, actually, that's a bit messy. Should have done that first. So 1 out the front divided by 2 pi. Sine becomes a negative cosine. There we go, and then the brackets stay the same, like that. But remember, we have that plus c. So this now is g of x. And so then we use this. So this is technically a coordinate, right? It says when x equals 1, y or g of x is equal to 1 on pi. So we're going to sub in the point 1 and 1 on pi into our function, and we should be able to use that to solve for c. So 1 on pi is equal to negative 1 on 2 pi. Cosine 2 times pi times 1 plus c. So 1 on pi is equal to, that's a bit wonky, is negative 1 on 2 pi cosine 2 pi plus c. Here we use our exact value, so cosine of 2 pi is 1, so we get 1 on pi is equal to negative 1 on 2 pi times 1, so just that, plus c. So c is equal to 1 on pi plus 1 on 2 pi, which then we have to make the denominators the same and all the rest of it. So this here would be 2 on 2 pi plus 1 on 2 pi, which is equal to 3 on 2 pi. And there we go. And so always check, it is asking us for g of x, so then we'd have to state that. So g of x equals, now that we've got c, it's going to be negative 1 on 2 pi cosine 2 pi x plus 3 on 2 pi. And there's our g of x. And there we go. So that's everything through it. Obviously, first principles doesn't get asked a whole lot, but it's really good to understand it because it kind of gives the background behind all of the applications, the concepts of areas under the graph, and it's also used in probability, which you've probably already realized, in terms of continuous distributions, using the area as being the area under the graph of a PDF as being the probability of x, taking the value within those bounds. So first principles just explains where the theory comes from, and that if we theoretically reduce d of x approaching 0, just like we had it approaching 0 in the case of derivatives, then we can get a much more accurate measure. We eventually just kind of throw that in the bin though and follow the formulas, but you won't really understand the mechanics of the formulas if you don't understand the first principles. And there we go. That is everything for anti-differentiation. If you haven't already, I did another one running through the probability question from the 2018 VCAR exam that might be of a lot of help. Let other people know about the videos that I'm making as well, because I'm assuming that they're going to be of a lot of help. At the moment, I'm just kind of following the requests of my own private tutoring students as well. But if you're interested to see anything in particular, let me know. There's a fair focus on maths at the moment, being further maths and maths methods. But obviously I covered pretty much every single VCE subject. So biology, chemistry, physics, psychology, health and human development, business management, economics, English as well, standard English, a little bit of literature, don't touch English language. A whole bunch of other ones as well. So if there's anything of interest, let me know. And otherwise, I will see you in the next one.